Thank you, everybody. Yeah, I'm a bioinformatician, so I work in the field of what's called surveillance, trying to pick up on these new variants as they're showing up. But so let's start with the virus, and I think everybody's seen this kind of picture before. So the virus is this really, really tiny ball. You know, these things, this virus, the SARS-CoV-2, as we call it, the one that causes COVID-19, is about 100th, only about a 100th of the size of a human hair, even smaller than that sometimes, okay? And it's covered in these things that we call spikes. They call them spikes, but to me, they look more like trees. So these little bumpy things over here that are red in this diagram, okay? And those are used to connect to our cells. So the virus is floating around there, and then if it bumps into the right kind of cell in our body, it uses these spike things to kind of latch on, and then it can get into the body. And then when it does that, it turns our cells into a little virus factory. So it starts using our cells to make lots of copies of itself. Okay, so what is it copying? So if we, inside the virus, inside the ball, there is a thing called the genome. It's a recipe book for how to make viruses. So once it gets into the cell, it uses this to make lots of copies of itself. But when it's making these copies, it's a bit like if you're taking a photocopier and you're copying a document. When you copy the document, you don't make a perfect copy. Maybe there's a bit of dust on the photocopier or something like that. And if you look at a copy of a copy of a copy of a copy, or if you're old enough to remember tapes, when we used to get copies of tapes, then the viruses are a little bit different from each other when these copies are being made, okay? And inside every person who's infected with this, in other words, who's getting COVID-19, there are many, many copies of the virus floating around, actually millions of them, okay? So because the copying is not perfect, that's how we get the so-called virus variants. So it's a process that we call mutating, okay? And these virus variants form family trees. So, here's a picture of a family tree. You can think of, somebody and their children and children's children, things like that. And just like with our human families, I look more similar to my mother and my father than I look to my grandparents and my great-grandparents and great-great-grandparents look even more different. So as you go across generations, then the virus starts looking a little bit different to what the original virus looked like, okay? And these changes that are happening, they're kind of random, but remember, this isn't happening on its own, because all the time that this is happening, the virus is making copies of itself, our immune system is fighting the virus and trying to kill that virus. And of all these different copies, some of them will fight our immune system better than others, okay? And the ones that fight our immune system, or maybe the ones that spread from one person to another better than the other ones, then they start, most of the viruses start looking like the successful viruses. And that's how we get what's called variants of concerns. Now, you've heard some of these names: Alpha, Beta, Delta, and now we've got Omicron, okay? And all of these so-called variants of concern are types of the virus. In other words, descendants of the virus, copies of the virus that have something a little bit different about them that makes health authorities worried, okay? Delta is particularly well known for spreading better than other variants, and Beta was known for fighting our immune system better, okay? And where are most of these changes happening? Remember, I talked about that thing that they call a spike, but I say it looks like a tree. This spike is where a lot of the changes are happening. So this is a picture of the spike just taken on its own without the rest of the virus. And you see here, it looks a little bit like a tree at the top here. And this top part, the top part of the tree is what connects to our body when the virus is getting into us, okay? So when our body learns how to fight the virus, or when we get immunized and therefore we're training our body to fight the virus, it's really learning well how to fight this spike, okay? And it's going to try and stop the spike from doing its job of getting into our cells, okay? Now, if we look at the thing that gets called Omicron, that's a version of SARS-CoV-2 that has a lot of changes. It's not a great picture here, but these orange bits are all the changes that Omicron has on the spike. So at the top of the spike, the bit that starts connecting to our cells, Omicron has changed quite a lot compared to the original virus that we first saw last year. And we think that those changes are going to let Omicron fight our immune system better, okay? Now let's just step back a little bit. We don't know exactly where Omicron came from. It's been found in a number of different countries. We do know by looking at the family tree and how different the different Omicron viruses are, that this thing arose about 2 months ago. So we think somewhere around the start of October, then the first Omicron version of SARS-CoV-2 was in somebody and it spread to other people, and now it's spreading fast around South Africa, okay? But we don't know whether it started in South Africa or Botswana or Nigeria or the Netherlands or somewhere else. We just know that it's here and it's spreading, and it's got all these changes here on the spike. And I said our body is fighting this thing, and it's fighting this thing. The first way it fights it is with a thing called antibodies. And antibodies are these tiny little particles that stick to the virus. So, very importantly, they stick to the spike, and they stop the spike and the virus from being able to do its job. And once the virus is all like kind of stuck down with antibodies, then the rest of our body's immune system can come up and sweep up these disabled viruses and clean this thing out of our system, okay? But when the virus is changing, and the viruses that are better able to fight our immune system, they're better at fighting these antibodies. And many people have had COVID-19 in South Africa. Quite a few people have been vaccinated, and now the virus is like really the ones that are fighting our immune system, they've got a better chance of succeeding. So we think that's why Omicron is doing so well at the moment at infecting people, okay? So if the spike changes enough, it can hide a little bit from, or more than a little bit from these antibodies, okay? And if that happens, then you might get infected with COVID-19, will get the disease COVID-19, get infected with SARS-CoV-2, even though you've had COVID-19 before or you've been vaccinated, okay? But this is not our only line of defense, okay? The next thing that can happen, if the virus gets past the first line of defense, these antibodies, there are these other cells in our body called T cells. And anybody who's dealt with HIV will have heard a lot about T cells. And what T cells do is they find the virus factories. Remember, I told you that if the virus gets into one of our cells, then it can turn that cell into a virus factory, okay? And what the T cells do is they go find the virus factories and they shut them down, okay? And the thing with this is that you might then get infected with COVID-19, but because the T cells are shutting down the virus factories, you wouldn't get very seriously sick. And this is, obviously good news. So Omicron might be able to get through the first line of defense, but almost certainly will not get past the next line of defense, okay? And this is also very important that the infection starts here by your nose and your mouth, and then it goes down to your lungs. And because we've got an immune response from the vaccine, then that can stop the infection getting deep into your lungs and causing the kind of severe disease or even death that we've seen, okay? So there's a problem though, because if the virus is able to infect us, then it is still able to spread, even though we've been vaccinated. So we don't know how well exactly the vaccines will work against stopping infection. We almost 100% certain that they'll carry on working against stopping severe disease. But if the vaccines are not working that well at stopping infection, then COVID-19 could carry on spreading even if we've got vaccinated people. So what can we do about this? Okay, and this is my last slide, so I'm going to stop sharing to save bandwidth. So what can we do next? Okay, the one thing is that the vaccines that we've got at the moment, they're the so-called first generation of vaccines, and there's lots of people working, and this is mostly not in the pharmaceutical companies. These are researchers working often in universities or government labs, working on better vaccines. So they might make a vaccine that is a so-called booster. A booster vaccine, however, would be the same kind of vaccine given again. So in other words, maybe 6 or 8 months after getting your first dose, you get another dose of vaccine. And what that does is it increases the antibodies. Yeah, okay, I can start my video. I was trying to save everybody's bandwidth, but okay. The booster vaccine could increase the amount of antibodies we've got, and then that'll stop infection, before it even gets a chance to start. But the other approach that people are looking into is making new kinds of vaccines. So maybe vaccines that are tuned against some of these variants of concern, like Delta or Omicron, and then will be better at fighting these specific variants. Or maybe a vaccine that specifically targets your nose, that you spray in your nose, that can actually make you stop the infection before it even gets a chance to get going. But the thing is this, as we're going to hear just now from Lauren, just because the vaccines are being made doesn't mean that we're going to get them. Because we know that up until now, vaccines have been very unfairly distributed around the world. Okay, so what other tools do we have? Obviously, one of the important ones is masks, and good quality masks that cover your nose and mouth and can fit nicely. But just like, and with vaccines, masks are also not evenly distributed. We don't all have equal access to them. And I mean, this is really unfortunate, and because masks can stop not only the spread of COVID-19, but they can help us stop the spread of diseases like tuberculosis, influenza, and so on and so forth. On the other hand, because of the other problem we have besides the fairness angle of masks is that there's what we call stigma, that, when you're wearing a mask, people can think, well, you're only wearing a mask because you're sick. So then people can react quite rudely to somebody. But there's, so all the other tools we've got, so masks, staying away from each other when we're sick, getting access to tests so that we can find out quickly that we are sick, even showing up at hospital in time if we are seriously ill. These things are all facing the same problems of unfairness or inequity in the health systems that we've got with the vaccines. So the fighting to increase fairness around health provision is a crucial tool to stop COVID-19. Okay, but anyway, so I think that's enough about what are these variants and a little bit of where they came from and how do they work and what can we expect from them. We will learn a lot more about the science of them in the next weeks. I mean, scientists are working incredibly hard. Well, actually, I'm one of them, but yeah, and my colleagues are working incredibly hard to try and understand exactly what these new variants mean in terms of the science, but that will take a little bit of time.